Imagine a world beyond our senses, a world so small that the laws of physics as we know them break down. This is the microscopic realm, where the rules of classical mechanics no longer hold sway. Here, energy doesn't flow smoothly but exists in discrete packets like tiny bundles of light. Particles behave like waves and waves act like particles, defying our everyday intuition. This puzzling behavior, unexplained by classical physics, set the stage for a revolution in scientific thought, the birth of quantum mechanics. This strange behavior wasn't just a theoretical curiosity, it had profound implications for our understanding of the universe. It underpinned the very structure of atoms and the interactions of light and matter. It was clear that a new framework, a new set of rules, was needed to understand this hidden world. For centuries, classical mechanics, spearheaded by Isaac Newton, reigned supreme. It explained the motion of planets, the swing of pendulums, and the trajectory of projectiles with remarkable accuracy. It provided a deterministic view of the universe, where the future unfolded predictably from the present. However, this elegant framework faltered when confronted with the microscopic world. The first cracks appeared in the late 19th century. Physicists studying the behavior of light encountered perplexing observations. Classical physics predicted that heated objects should emit radiation at all frequencies, leading to infinite energy, an impossibility known as the ultraviolet catastrophe. This contradiction highlighted the limitations of classical mechanics and hinted at a deeper, more fundamental theory governing the universe. Enter quantum mechanics. In the early 20th century, a new generation of physicists, dissatisfied with the limitations of classical physics, embarked on a radical journey. They proposed a revolutionary idea. Energy, instead of flowing continuously, existed in discrete packets, or quanta. This seemingly simple concept had profound implications, challenging the very foundations of classical physics. This radical shift in perspective did not come easily. It required a fundamental change in how physicists viewed the universe. Instead of precise, deterministic trajectories, quantum mechanics embraced probability and uncertainty. It proposed that the act of observation could influence the state of a quantum system, a concept that seemed counterintuitive but was borne out by experiments. Section 4: Pioneers of the Quantum Realm, from Planck to Bohr. The development of quantum mechanics was not a solo effort but rather a symphony of brilliant minds. Max Planck, in his attempt to explain the spectrum of black-body radiation, introduced the idea of quantized energy, laying the cornerstone for the quantum revolution. Albert Einstein, building on Planck's work, explained the photoelectric effect by proposing that light itself was quantized, composed of particles he called photons. Niels Bohr further developed the quantum model of the atom, proposing that electrons orbit the nucleus in specific, quantized energy levels. These pioneers, along with many others, pieced together the puzzle of quantum mechanics, revealing a universe far stranger and more wondrous than anyone had imagined. Section 5: Quantum Mechanics in Action Technology Shaped by the Subatomic. The impact of quantum mechanics extends far beyond the realm of theoretical physics. It underpins many technologies that define our modern world. Semiconductors, the heart of computers and smartphones, rely on the quantum behavior of electrons. Lasers, used in telecommunications, barcode scanners, and medical procedures, operate on the principles of quantum emission and stimulated emission. Quantum mechanics is not just about understanding the past and present, it holds the key to future technologies. Quantum computing, still in its infancy, harnesses the principles of superposition and entanglement to perform computations that are impossible for classical computers, potentially revolutionizing fields like medicine, materials science, and artificial intelligence. Quantum cryptography promises secure communication channels, unbreakable by even the most sophisticated hacking techniques. Quantum mechanics is more than just a theory, it is a fundamental framework for understanding the universe at its most fundamental level. It has revolutionized our understanding of the microscopic world, and has led to groundbreaking technologies that shape our daily lives. As we continue to explore the quantum realm, we can only marvel at its elegance, its strangeness, and its boundless potential to unlock the mysteries of the universe and drive technological innovation for generations to come.